Buongiorno, ben ritrovati. Good morning. Welcome back to Plasma Physics. Can you hear me?
Yes.
Hello. Good morning. Okay, can you see the tablet as well?
Yes.
Excellent. And so we can briefly see what we've seen last Monday. We started talking about waves, in particular, in general, 1D waves, the wave equation, the progressive solution, the regressive one, the superposition principle, and especially we introduced the concept of dispersion relation, which is the relation that links the k number of a given wave solution to the angular frequency of the wave, the omega one. So let's see if we find, okay, this is an example of a dispersion relation, the one we are going to see today as well, in many different forms. So we have something that links the omega, the angular frequency, to the k number, so the wave number of the wave. And there are two important classes of media. The ones that don't have any dispersion, so for instance, they don't have this constant term here. And basically, we see that the phase velocity and the group velocity are the same. So the dispersion relation in the omega k plane is represented by a straight line. In that case, the wave packet is represented by the wave is not distorting, because the phase of each component of the wave is traveling in the medium at the same speed of the other ones and the neighboring components. So we have a no dispersive medium, and the packet is rigidly advected in the direction of the wave. Instead, here we have, for instance, this one here, which is a typical dispersion relation for a plasma. We have a constant term, which in a plasma is typically represented by the plasma frequency of electronic oscillation. And we see that the dispersive relation becomes like a curve, and is being a curve, the slope of the curve is changing, is not always is constant. So we see that the slope of this curve is represented by the group velocity. And the most important point to highlight here is that for zero k vectors, so for very long wavelengths, the slope of the dispersion relation is 0, telling us that the wave in this condition here does exist, but it's not a wave anymore in the normal sense. It's just a local oscillation. For instance, an oscillation of the plasma frequency. And then we've seen that by increasing the k number of the vector, it means by reducing in the other direction the wavelength of the solution. So going to shorter wavelengths, we've seen that the dispersion relation in this case is approaching that one of a non-dispersive medium. And we recover the fact that at a high frequency, all the wave components are traveling at the same speed. And v squared here is the characteristic speed of the wave in the considered medium. For instance, in vacuum, we'll see that this is for electromagnetic waves. So light solution will be representing c squared, so the speed of light. Okay, then we introduced the linear theory, the concept of expressing a given dynamical quantity as an equilibrium state, and plus a small perturbation with respect to the equilibrium state. And the wave solution, what is actually propagating in the medium in the form of a wave, transporting energy and momentum, is the small perturbation. In this framework, we then linearized and switched to complex notation by expanding any possible waveform, in this case here, a wave in space, in 3D space and time, as the superposition of many plane waves, okay, which are planes of equal phase in the direction of the planes orthogonal to the direction of the given wave solution, which is represented by the wave vector. So the wave vector K is made of two important information combining together. One is the modulus of the K wave vector, which is the wave number telling us the wavelength of the considered wave solution, and the other important information is the direction of the wave vector telling us in which direction the wave is propagating with respect to space. Okay, switching to complex notation, and we can rewrite differential operators in space and in time as multiplications by respectively ik for the space derivatives and I omega for the time derivatives. Okay, then we introduced the waves in plasma, and we stressed out the fact that a plasma is a collection of particles, ions and electrons. So we on top of the usual acoustic behavior, so a gaseous behavior where you have an acoustic waves, we have two more dynamical quantities taking part in the plasma evolution, and those are the electric field and the magnetic field. And coupling them together and to the plasma properties represented by the density current density J, we found out that we can couple this system of equation and seek for a solution, for instance, for the electric field. So we started, for instance, taking the curve of the Faraday's law, and we stopped at the end of last lecture with this equation, and this is exactly where we are taking over from this morning. And so let's briefly go over this derivation. So we have the Faraday's law here. We take the curl of both sides of the Faraday's law, and we exchange the curl, the special curl operator, with a time derivative, and we express using the Maxwell-Ampere's law. And when I'm saying that, it's just to remember that this is the Maxwell term, is this displacement current, and this the original Ampere's law due to amperes, taking into account that the sources of the magnetic field are the currents inside the medium, inside the plasma in this case, electric current. Then what we do, we apply the time derivative to both terms, and it was important to remember that mu naught epsilon naught is exactly the definition of the speed of light in vacuum. So this is expressed, let's say, in general physics 2 terms, nothing new. What we added is we go to complex notation, and going complex notation, I remember, is like expanding into plane waves and working only with the amplitude of a single component. And we are still in 3D space for this case. And what we do, we linearize at the same time So we switch to complex notation, as you can see here, and we drop the equilibrium state, and we focus only on the perturbation. So we translated this into complex notation. So for every nabla operator, we have the multiplication by ik, I times the imaginary unit times the wave vector, and we substitute for E, which is the overall electric field, we take just into consideration the perturbation, since we are seeking for a wave solution. Okay, then we have the second derivative with respect to times. So I omega times I omega, which makes minus I omega square, and still the perturbation in the electric field. And then we have the time derivative of the current density, expressed using the microscopic Ohm law in this form. So J is sigma times the electric field. And sigma is a complex quantity, and depending on the frequency, is the conductivity of the electrical conductivity of the plasma. So let's keep on working on this equation. So I copied it here back, and today is the last day of April. Let's put it in here. It's 30th of April 21. Okay, and what's next? We define a what is called a dielectric function, collecting these terms here that are in front of the electric field. So if we define the dielectric function epsilon, sorry. So this is dielectric function. Is defined by 1 plus I mu naught, the vacuum permittivity, times speed of light squared divided the omega of a given wave solution, times the conductivity, which, if you remember, in a non-magnetized plasma can be expressed as a function of the solution as well. So it's depending on the frequency of the phenomenon we are considering. As you can see, this is reminding us of epsilon, the dielectric constant. Epsilon naught, if you remember, is the, where it is, okay, this one, this symbol here is the dielectric constant of vacuum. Epsilon r is the relative dielectric constant with respect to vacuum. But this, now we introduce something which is more or less has the same meaning, but instead of a constant is defined as a function, because as you can see here, is depending mainly on the frequency of the wave we are considering. Okay, if we use this dielectric function, then we can write our equation into, okay, this is becoming minus. So I squared makes minus, then we have the product, vector product of K wave number times K times the electric field perturbation is equal to, we can collect an omega c squared factor in front of it, and then the other two terms are becoming the epsilon function, the electric function epsilon, times the amplitude of the electric field perturbation. Okay. Now we have k vector e. Obviously, there's the order of the vector operator is important, because if you do first the the first vector operator is identically 0, so it's obvious that we have to do the operation in this order here. Okay, and we recall a useful relation between a curl of a given quantity, which is very often used in wave equations. So we can write, let's say, the curl of a vector quantity A is curl of A equals the grad div minus the Laplacian. So is the gradient of the divergence of a given quantity A, could be the electric field, could be the magnetic field, minus the Laplacian, so nabla squared of the vector field A. And if we translate this into complex notation, then the same differential equation becomes, we can write it in two steps. So we have ik times ik times A equal ik, which multiplies ik dot A minus ik squared times A. And by collecting and multiplying the imaginary units, we end up with, okay, on the left we have I, so it becomes minus k times the vector field A equals, on the right hand side we have I squared again, so it becomes another minus sign, k times the scalar product of k vector with A, and then we have plus here k squared, the square of the wave number times A. Okay, this is the translation of a well-known differential operator identity applied to a vector field in terms of written in complex notation. So now we can plug this equation here into our equation. So basically we substitute for this term into our left-hand side term. And let's put a timer before switching to the new page. So we, it's 34, we take a break at 9. Yes, okay. So our wave equation becomes minus k which multiplies the scalar product of k and the electric field perturbation. Then we have to change all the signs because we have in front of here a minus. So this becomes plus and this becomes minus. Okay. Is that correct? Let me check. That one. Yes, that should be okay. The only thing is that we have a minus here. Okay, it becomes a plus. And we have this term. Okay, let's see. At the end, we'll see if all the signs are correct. So we have a plus k squared electric field times the electric fields equal to omega squared over c squared times the dielectric function epsilon times the electric field E1. Okay, this is important. So we highlight it, and is the general form of a wave in a plasma in terms of the electric field. Okay, so what we have to seek for a solution. So we have to find which k and omega in our dispersion relation are fulfilling this this relation, which is a constraint that links omega and k. Solution to this equation are represented in the omega k space by the dispersion relation. So points that are satisfying the wave equation are making up what is called the dispersion relation that we have represented the other time. So what we want to do? This equation itself can describe many different waves and different propagation modes. So it's very rich. We want to decompose it and see how to tackle or describe, let's say, different waves in the plasma. For sure here, what is natural to see is that there's a relation between the k vector and the electric field direction. The E1 is the perturbation to the electric field, and this is going to represent what actually is propagating inside the plasma. And the k vector has in itself the wave number, so the wavelength of the wave and the direction. And this term here is a spatial term that tells us in which is the relation between the k vector and the let's say and the electric field vector. So we can easily divide the problem in two classes. So for solution where the electric field is propagating along the k vector, so we will call them these longitudinal waves when the electric field is in the propagation direction of the wave. And obviously the opposite one is when the electric field is orthogonal, it's perpendicular to the direction of wave propagation. In that case, we call them transverse waves. So let's see the first class. So we, for instance, we assume or we seek for solution where the k vector is orthogonal to the electric field. In space, it means that, for instance, if this is the direction of wave propagation, the electric field is oscillating in the perpendicular direction. Okay, it's not very perpendicular. Let's do it again. Maybe like this, better. And this is A1. As you've seen, I put a back-to-back arrow to mean that actually this is the k is the propagation direction of the wave, and the electric field will be oscillating up and down in a perpendicular direction to the k vector. So when we build up the electric field in space, we'll see that the electric field will be oscillating this way along the propagation direction. So this is it's called a transverse waves case. Transverse waves. And if we were in vacuum, for instance, this would represent the electromagnetic waves that you might remember that in these waves, and we're going to see this again later on, maybe today, the electric field and the magnetic field are oscillating at 90 degrees from of each other, and they are both defined in the plane which is normal to the direction of the wave propagation. So these are transverse waves. In that case, if k is perpendicular to the wave, then you see that this scalar product becomes 0. So this term is 0. And we can say that then we have that k squared E1 is equal to omega squared over c squared times the dielectric function times E1. And solving for, seeking for a solution, we see that the dispersion relation becomes k squared equals omega squared over c squared times epsilon. Okay, and this is a dispersion relation that links k and the omega of the wave. And you see that the presence of the medium is contained, fully contained into the dielectric function that we defined earlier on. So we have a constant term, and then we have a omega dependence on the electrical conductivity of the plasma. Okay, the other solution is when we have, instead of a perpendicular oscillation of the electric field, we have that the electric field is parallel to the wave vector. So we seek for a solution where k vector is parallel to the electric field. And if we were going to represent these waves again, so we have the k vector propagation direction. In this case, the electric field will be oscillating up and down along the direction of the wave, E1, okay? And as you can understand, these waves gets called longitudinal waves. For longitudinal waves, we have that k equals k times the k vector, okay, and E1 equals the amplitude of the oscillating electric field, and the direction is the same because the two vectors are parallel. So in the our wave equation here, these terms becomes that we have minus k that multiplies the dot product of k and E. So we have k times E1, k dot k. So the scalar product of the k vector of the k versor with itself. Then we have plus k squared E1 times the k vector, and we see that the first term is becoming minus k squared E1. This term is exactly 1, and we have the direction of the propagation here, plus k squared E1, and again the direction of propagation, k hat. So you see that this is exactly 0. So the left-hand side of our wave equation is for longitudinal waves. So this part here is exactly and identically 0. So it means that the right-hand side term is 0. So 0 equals to omega squared over c squared epsilon E1. So in order this to be a non-trivial solution, where obviously if the electric field is 0, E1, it means that there's no wave, okay? So if we seek for a non-trivial solution, omega is different from 0, this is a constant, then we see that the wave solution are contained in the solution of the dielectric constant epsilon equals to 0. So the dielectric function equals to 0. Solution of this to this equation are giving us the omega and k, so the dispersion relation for longitudinal waves. Okay, so we are ready now to solve these two cases, so the longitudinal and transverse waves, and we'll start with longitudinal waves in plasma. And we'll see that we'll look for two kinds of longitudinal waves in our course, the electrostatic waves and ionostatic waves. So the one that take as a partner the electric field and with respectively the electrons or the ions. And then we see a solution for the transverse waves, which is going to be the electromagnetic wave solution in plasma. So let's start with the electrostatic waves. Electrostatic waves in plasma. These are longitudinal waves. So let's remember what this means. It means that the k vector is parallel to the wave solution for the electric field. And if this is true, what would it means that, let's have a look at the curl of E. Curl of E1 equals, can be expressed as I k cross E1. But since we are seeking for longitudinal waves, so for a solution where k is parallel to E, the cross product, the vector product, is 0. Because k and E1 are parallel. But if you remember, the curl of E is, using Faraday's law, is the time derivative of B. Equals minus the time derivative of B. And pay attention to the fact that I'm using the one index, reminding us that we are working with the perturbation, the small perturbation to the electric fields and the magnetic fields. Okay, E1, B1. So this okay, more than equal is leads to, okay, in the same way that the curl operator can be expressed in complex notation. So this is 0, so it means that using Faraday's law, the time derivative of B is 0. And what does this mean? It means that B1 is constant. With respect to time. And being constant with respect to time, it means that it's not oscillating, it's not propagating. So actually, it's not part of the wave solution. And that is why in this term, electrostatic waves, there's this static that it means that B is not propagating. So the only partner in the wave phenomenon is going to be the electric field. It's only the electric field that is going to propagate as a wave, and no magnetic field will be propagated. So the static terms, it means that it's referring to the fact that B is not propagating. Electrostatic is a jargon term is not that we are using in plasma physics. Electro means that it's going to involve the electric field and the and in our case the electrons. But you see that only the E field is propagating. E is propagating. Okay. And now we have to see how to couple the electric field E1 to the medium properties, so to the plasma properties. There are many ways of connecting the electric fields to the wave, to the plasma properties. And the first solution we are seeking is involving just the electric field and the electron species. So in our first solution, we assume that the ions are at rest, are cold and at rest. It means they are basically fixed, they are not moving. And this is most of the time a very good approximation, because this is due to the fact that the electrons have a much higher mobility than the ions, so they respond to the phenomena on a much shorter time scale than the ions. And in this case, when we are talking about wave phenomena, usually are much faster than the thermodynamic scale. And to assume that the ions are at rest is usually a very good approximation, unless we want to describe something that involves the ions only. Okay, so among the electrostatic waves, now we focus our attention on the electronic electrostatic wave. So first case, is going to be the electronic, electrostatic wave, where this part here means exactly what we just described. So this is a longitudinal wave where only the electric field is propagating and the B field is static, is not moving. And then the electronic in front, it means that the electrons are taking part in the process. Electrons are interacting directly with the E field. Ions are at rest. This is because the mass of the ion is much larger than the mass of the electron. So what we are going to describe, the electronic electrostatic wave, is a fast oscillation with respect to ions motion. So we can neglect the fact that the ions are moving at the same time. It means what is happening is going to happen. The electric field is oscillating. An oscillating electric field will set up an electrostatic force acting on both charged species, so electrons and ions, but on the time evolution of the electric field oscillation, only electrons can respond, and instead the ions will see just an electric field flipping up and down very fast, so they will just oscillate on their own location without moving. So we can easily consider them at rest with respect to the electrons, obviously. This is not true in general, but with respect to the electrons, they can be considered at rest. So we need some dynamical equations. First one that we are going to use is Newton's law for electrons, and this is stating that mass of the electron times the electron density times the total derivative of the velocity field of the electrons on average. So you know that you've seen how to treat with MHD equation. This is the average velocity in a given point inside the plasma of the electronic distribution. It's equal to what? This is mass time acceleration. So on the other side of Newton's law, we have the forces acting on this small lump of electrons. And this is going to be, okay, almost to take a break, is the Coulomb force. So charge of the electrons times the electron density. So this is the represented charge, lump of charge. And on that, we have that the electric field, we can, for the moment, just drop this index here. In general, this is just true for both the equilibrium value and for the small perturbation value. And then, since we are in a plasma, we have on top of this Coulomb term, we have forces arising from the pressure gradient. So from that arising from the collision among the various species. So we have minus the gradient of the pressure of the electrons. So this is the Newton's law for the electrons. Then what we need? We need the continuity equation. So the first one is the dynamical equation. The second one is telling us that mass conservation law for the electrons. So we can write that the derivative with respect to time of the electron density in a given volume plus the divergence of the electron flux. So it's the density, local number density of the electron times the velocity of the electrons. This, as you remember from the transport lecture, is the I, is the number density, number current of for the electrons, equals to 0. Okay, this is the continuity equation. Continuity equation. And finally, we have to, so we have a dynamical equation linking the electric field and the electron species. We have a mass conservation law for the density of the electrons. And then we have a source term, let's say, for the electric field. So how can we produce the electric field that then is propagating? And we used Gauss law, so one of the Maxwell's equation for electric field. Gauss law, which is stating that the divergence of the electric field, so the source term for the electric field, are the charge density divided epsilon naught. So the charge density in our case is can be expressed as E times the elementary charge of the ions. Let's assume, for instance, a hydrogen plasma, so is the elementary charge of the proton, minus the charge density due to electrons, so minus E times the density of the electron. This is what is called in general physics 2, rho, is the charge density, divided epsilon naught. Okay, so we'll give a name and then take a break. So we have equation A, the Newton's law, equation B, continuity equation, equation 3, Gauss law. So it's the source term. Combining these three equations after the break, we'll obtain the wave solution for longitudinal waves in plasma, and we will get the dispersion relation as well. So let's take a break. Are there any questions? No? Okay. So let's take a break, and then let's reconvene here in 10 minutes time at 9:15. Okay, here we are again. Can you hear me? Are you still there? Is anyone there?
Yes, we can hear you.
Okay. So, what is our plan is to solve these three equations, and we want to seek for a solution solving 1D, which is one-dimensional, which is the dimension we want to use. Obviously, is the one in the direction of the wave propagation, where we have a k vector is identifying a direction, and the electric field is oscillating that direction as well. So the natural solution is to seek for something that is moving, is oscillating, is changing in time and space along the k direction. Okay. In this case, we are going to have, for instance, an x coordinate along the k direction, and kx is just becoming just k, and the component of the k vector will be the wave number as well, since we are reorienting our system of reference in the direction of the wave propagation. Okay, and we solve for 1D, and we look for a linear solution. So we linearize. So we expand around an equilibrium state, and then we move to complex notation. In order to change differential operators for multiplications. Okay, this is the plan. So first of all, let's linearize in 1D. What is our reference? So we state we linearize around a thermal equilibrium state. Thermal equilibrium. So we suppose the plasma to be in thermal equilibrium. It means that, for instance, the density, the pressure, and the temperature of the plasma are uniform. And this is important. Are uniform, so they are not changing in space, and the electric field is zero. So is zero. In a thermal equilibrium state, the macroscopic electric field is zero. There's no electric field. So the only component to the electric field will be the perturbation. So let's see how this comes along. So we have the density. Number density is going to be an equilibrium density, which is uniform, plus a small perturbation. Then we have that the velocity of the electrons is going to be perturbed around an equilibrium state, and in thermal equilibrium we do not have macroscopic motion of the species, so the equilibrium velocity of the electrons is zero. This is the average velocity of the electrons. You know that there's thermal motion of the electrons, but the mean speed of the velocity is zero in the frame of reference of the fluid. Okay, and we have the electric field would be an electric field plus at the equilibrium plus the small perturbation, and we just said that in local thermal equilibrium, there's no macroscopic electric field. So the only electric field will be arising from the wave phenomenon. So will be the propagation, the wave term. Okay, and in our equation, we have the velocity of the electrons, the density of the electrons, and the electric field. We consider the pressure we have to consider, and then everything else is already being said about. So let's discuss about the pressure. Pressure of the electrons will be an equilibrium pressure, which is not is different from zero, obviously, plus a perturbation term in the pressure, but being uniform, since we have that you see here, we have the pressure enters as the gradient of the pressure, and we are linearizing around an equilibrium state. So we can just already saying that the gradient of the pressure will be the gradient of the equilibrium pressure plus the gradient of the perturbation. But since we are in a uniform state of equilibrium, the only contribution to the gradient of the pressure will be coming from the perturbation of the pressure. That's because we are in a uniform equilibrium state. Okay. Then another manipulation that we need to is to talk about the time derivative, total time derivative of the velocity. This term is in the Newton's law here. See, this is the total time derivative of the velocity field, and this is corresponds to the partial derivative with respect to time of the vector field plus the advection term. So it's going to be V E cross dot nabla applied to the vector field itself. Okay, and this is the advection term in the total time derivative along the fluid element. So we have this term here. We are going to say something about this term. Okay, let's linearize. For instance, this equation can be written as the first is the derivative with respect to time of the velocity field. I'm going to drop here the vector notation, vector sign. Okay, you can drop it. Why? Because we are working in 1D, so the vector, the velocity vector and the electric vector will have just a component along the wave propagation, as we said. So we seek for a 1D solution. So we have the time derivative with respect to V1, so the velocity perturbation, plus the other term is going to be V1 dot time the space derivative dx, and this is not going to be a dot anymore, it's just going to be a multiplication in 1D of V1. And as you can see here, this is the second order term in the perturbation. So we drop it because this is a second order. So in the time derivative of the velocity field in 1D, what it remains is just the time derivative with respect of the velocity And the second term, which that is the advection term in the total derivative, is 0 because it has two terms of the first order. So we can neglect it when we linearize around the equilibrium state, retaining only first order terms. Okay. And let's move on. And another term that is important to describe is, as you can see here, in the continuity equation B, we have the divergence of the density times the velocity of the electrons. We can work a little bit on this term. So this is the divergence of NE times dE. And we linearize it as this becomes IK. I'm going directly to complex notation and linearize it. So we have that the density is N0 plus N1. So the equilibrium state plus the perturbation in density times V1, because the velocity is only the perturbation term, there's no V naught. And this then becomes IK times N0 V1 plus IK N1 V1. And as before, we drop the second order term. And all that remains is just IK N0 V1, which we can actually rewrite back as a normal differential operator as dx of N0 V1. Okay, this is the terms that remains in the divergence of the mass current of the electrons. Okay, now we are ready to rewrite the original equations. So A, B, and C, rearranging a little bit the terms. And we go directly to the linearized form of this equation. So let's rewrite equation A, Newton's law. So let's put a separation sign, and we start with, okay, let's say that A becomes, if we linearize and go to vector notation and complex notation, we have minus mass of the electrons times the N naught. N naught is both the density of the number density of ions and of electrons. Okay, is the equilibrium density times the I omega. Sorry, this is the time derivative with respect to is the time derivative V1. And then we have the let's see, the electrostatic force. And in these terms, since E is just the perturbation, only N0 survives in linear at first order terms. So we have minus E N naught E1. Then we have the pressure gradient. The pressure gradient was this one here. We see that only the gradient of the perturbation remains, and if we linearize that, that becomes minus I K P1, the perturbation in pressure. So we call this equation as A star. This is the A star equation. So the linearized and equation and expressed in complex notation. We do the same for B, and B was, let's go and see what B was, is the continuity equation. And we've seen this is the time derivative, and the flux, the divergence of the flux is just the time derivative of, is this one here? No, is this one? Okay, is the okay, the space derivative with respect to n0 times v1, and complex notation is this term. So what it remains is minus I omega time derivative of n1. So the time derivative of the equilibrium state is 0. So only the perturbation in density changes in time. Then we have plus ik, and I'm using this term here, n0 v1 equal 0. And we can express this solving for n1. So we can solve for the perturbation of the density. So we can write this as n1 equals to k divided omega times n0 v1. And let's call this B star equation. So it's the continuity equation from which we can express, we can get a relation that links the perturbation in density to the perturbation to the velocity of the electrons. Finally, we have the C equation, which was the Gauss law. And the Gauss law was the divergence of the electric field. So in 1D, it becomes IK times epsilon naught. We bring the epsilon naught at the denominator of the right-hand side to the numerator of the left-hand side, times E1. So this is the divergence of the electric field in 1D, in linearized and complex notation. It's equal to what? Let's see what we have. We have this density term. Let's write it. It is density of the ions which are not moving. So is E times the equilibrium state density minus E electric charge times n0 plus n1 for the electrons. So what it remains is just the perturbation in density and charge due to electron motion. Okay, and from this we can get an expression for E1. So the electric field E1 is going to be I. Then we have the electric charge divided by K epsilon naught that is coming from the left-hand side. And then we have N1. Let's write it. N1. And we can use N1 from equation B. And we'll plug it in here so we can have it. We can write that the electric field is equal to I E divided K epsilon naught times K omega N0 V1. So we can, you see that there's a K that goes away. And all that remains again is I E times epsilon 0 times omega, which is the omega of the wave, the angular frequency of the wave, times n0 times v1. And we call this equation, let's call it C star equation. Let's have a look. We have a B star equation that we already used in inside C here, and C star equation now express a relation between the electric field and the velocity field of the electrons. And A star still contains V1, the A field, and P1. So we can solve for V1 and plug it in here. So we can have just two terms that are expressed as a function of electric field. What is missing here is P1. Actually, what we are going to do is express everything else as a function of the velocity, V1. So let's work a bit with the pressure term, because we need help from the thermodynamical properties of the plasma in order to link the perturbation in pressure to, let's say, the perturbation on density and other parameters of the electric fluid. So what we do is to study the pressure term. We are considering very fast solution of wave solutions are moving fast with respect to thermodynamic equilibrium times. So in terms of thermodynamic transformation, the sudden compression and expansion due to the wave motion is adiabatic. So it's a adiabatic transformation during which the electron fluid doesn't have time to exchange heat, so or to change its own temperature. So we can define the transformation corresponding to the wave phenomenon as an adiabatic transformation. So we use an adiabatic and this is the same that happens for acoustic waves, for instance, in a gas, where the transformation that links different points and states in an acoustic wave propagation are linked by an adiabatic transformation. So for an adiabatic transformation, if you remember, P times V to the gamma is V to the gamma is constant. This is the ideal ideal gas equation of state, and this is an adiabatic transformation. And if we express V, the volume of the gas, instead as a function of the number density, we can rewrite an adiabatic transformation as n to the minus gamma equal constant. Okay. This is the adiabatic transformation. And let's differentiate this. And by differentiating, we take dn times n to the minus gamma actually we can write it in this way. P is equal to a constant times n to the gamma, and gamma is the adiabatic index, so the ratio of the constant pressure, what is called Cp over Cv. This is the definition of gamma. A specific heat, okay, molar specific heat at constant pressure divided at the molar specific heat at constant volume. This is the adiabatic index. So we differentiate this, we get that an increment in pressure is equal to a constant times gamma n to the minus gamma dn, a perturbation in density. And what is dp? dp is just the difference between a final state, which we can describe as P naught plus P1, the equilibrium state, minus the plus the perturbation, minus the equilibrium state. So this is the difference with respect to the equilibrium state. So dP correspond to actually the pressure perturbation, and at the same time we have that dN, the differential of the density, equals to n0 plus n1 final state minus the equilibrium state, equals exactly to the perturbation. So we can write our equation here as P1, the perturbation in density, is equal to a constant times gamma times n to the minus gamma, and we can multiply and divide by gamma this thing here by n, sorry. So this I forgot in the derivative, no one noticed it, but there's a gamma minus gamma minus 1, and yes, there's a, I think that most of you are sleeping. You didn't notice that the derivative was actually completely wrong. Okay, so we have gamma times n divided minus gamma. So if we divide it and multiply by gamma, by n, sorry, here, we can get on top constant time n to the gamma is exactly p, and we can rewrite our equation as p over n times gamma times dn. Okay, so we can actually simplify our notation, going from this term here into what we have terms, which is gamma and P1 over N0 times N1. Okay. So is that correct? There's P1 and we have to use the fact that actually we use the ideal gas equation of state, and for the ideal gas equation of state, we know that the pressure is equal to the density of the electrons equal to the density of the electrons times kT, Kb, called Boltzmann constant, times the temperature of the electrons. Okay, so we can say that in the end, dP equals P1, and by plugging in this function here, we can have on top gamma that multiplies kBT divided nothing times n1. Okay, actually this term here is, you see that if we divide the pressure by the electron density, as this term here, we can just easily write that this term is kBT n1. So I mixed a little bit things, but the important thing is that we're using an adiabatic transformation. We use the ideal gas equation of state that links the pressure to the density and to the temperature. And finally, we found a relation between the perturbation of the pressure to the perturbation of the density and the temperature of the electrons. Okay, so we have this term right now that we can plug into our A star equation. What time is it? Okay, almost ready to finish this derivation. And let's put everything inside this function here, inside this equation, substituting, for instance, C star, which gives us electric field as a function of V1, okay, in here, sorry, and P1. So let's rewrite A star and see what terms we need. So the first one is just, it's okay, minus M E and 0 times I omega, the time derivative, times V1. Okay. Then we have on the right-hand side the electric field term, and we use C star. So we have minus E and 0. And E1 was, let's take it, is this one here. I just copy. Okay. Sometimes with this rather long derivation would be much easier to have the blackboard as we used to have in our lecture hall, instead of flipping here and there equations. And then I need the last term, and the last term is minus ik times P1. And the last term is minus ik and times, and P1 we just got it from here. So we take it and plug it in here. I hope that everything is in place. Let's check. So we have okay. One, there's a bit missing. You see here that we have V1 here, V1 here, but we have N1 here. So we have now to use B star relation. Okay, this one here. That was telling us which is the relation between the perturbation in density and the velocity. So we take this one here, copy and paste it, oops, at the end here. So let's take this out and add this term. Okay. Now, we have, let's have a look at this equation. I move it a little bit in the center. Okay. Oops. Like this. Okay. We have dynamical properties. So we have V1, E1, N1. In this combined equation of the three we started from, we have V1 here, V1 here, and V1 here. So actually, we can drop the velocity, and then nothing else remains. All the rest are property of the plasma, which will be leading us to the dispersion relation. Then we see another thing that we have N0 here, N0, N0, another common factor that we can drop. Okay. And now we play a bit with this equation, and we multiply everything by omega divided, and we have another divided by ME, and yes, before that we see another common term is I, the imaginary unit. We have it here, here, and here, one. Then we change side to everything. So let's use a different color because all the terms are negative. So we have plus, plus, we multiply by -1 both sides. And then we have on the left, what it remains is just ME times omega. We want to get to a dispersion relation. So we want to have omega square on the left-hand side. So we multiply by omega and divide by mass of electrons. And what we get is, let's see, we have omega squared on the left-hand side, and then we have here that we get N0 E squared divided ME epsilon naught, okay, plus here we have that we multiply by omega, so this term goes away. At the denominator we're going to have the mass of the electrons, and we get gamma KBTE over ME times, we have a K here and another one, so K squared. So almost there. What we can observe that the first term here that we obtain is nothing else than the electron plasma frequency. Okay, so this is omega P squared. One of the first property of plasma that you obtain at the beginning of our course. And this is the frequency of the electron oscillation in the plasma, called the plasma frequency. And what is this second term here that multiplies K squared? This is KB T times a gamma in front of it divided ME. This is reminds us of the root mean square velocity of the electron. So actually, this is the thermal velocity of the electrons. It's proportional to it. We call it V0 electrons squared. Instead of having the thermal velocity would have a 3 factor in front of it, if you remember. Here we have a gamma, so it's very close to the thermal velocity of the electron, this characteristic speed, and we see why we call it characteristic speed. So if we combine and rewrite this equation, we can get the dispersion relation for our waves. So we have omega squared equals omega p squared plus d naught e squared times k squared. And finally, this is the point where we wanted to get. This is exactly the dispersion relation for electronic electrostatic waves. Let's analyze a little bit the structure of this dispersion relation. We have omega squared on one side. On the other side, we have k squared. We have a characteristic velocity that multiplies the wave number. So this is going to be the asymptotic speed of waves for very large k numbers. And then we have a constant term in front of it that we were anticipating last time. So we see that this actually is a dispersive medium, because the speed of the phase velocity is different from the group velocity. We can represent this as, and let's write it here again briefly. Omega squared equals omega plasma squared plus V naught squared of electrons times k squared. And in our plot, where we have omega as a function of k, we can represent this dispersion relation. So we have k and omega. We have our reference point here corresponding to, let's write like that, to omega p, the omega frequency, the plasma frequency, sorry, and the curve. You see that is the usual almost parabolic curve. It's parabolic in at the origin, so for k equals 0, and then tends to asymptotically to a linear function. So we have the asymptotes here. Let's draw them like, was it, I remember it was blue for the progressive wave. Okay, let's have it very thin line. Okay, and the asymptotic regressive wave, and our relation is represented by, oh, no, the other way, sorry. Okay, we have the right branch and the positive branch and the negative branch, they are symmetric. And this is actually the dispersion relation we introduced for non-dispersive medium. Okay, so we see that, and we'll take over from here next Monday. We see that for very large K, so for very short wavelengths, the plasma is becoming a non-dispersive medium, and the waves are traveling at v 0e, so this characteristic speed of the electrostatic waves in plasma. And when we reduce the K vector, so we go to longer wavelengths, we see that progressively the slope of this dispersion relation drops, going to 0. And when we have a very long wavelength, these wavelengths are not traveling anymore. The group velocity is 0, and these wave here are a static oscillation of the plasma, corresponding to the electrostatic oscillation that you studied at the beginning of the course. Okay, we drop it here, and we see each other on Monday. I'll stop the recording. If there are any questions.